Good evening, Anish. Can you hear me?
Good evening, sir. I can hear.
Okay. Uh, so we are in the week 8 of this course. So uh, the course is on finite element method and computational structural dynamics. As you know, we are discussing about uh, we were discussing about the 3D finite elements and 2D finite elements and element distortion and parametric mapping. So all these issues were discussed in the last week. So and there was a little introduction to shear locking, parasitic shear, these kind of uh, things in the week 7. So and like week 8 is continuation of the that, and in addition to that, we are also uh, going to see finite element per plates. So similarly, like you can extend it also for plates and also shells. So depending upon your interest, if you want to read, like that is an extension that you can consider reading. So what is shear loss? So if I have, let's say, a beam like this, and if I take an element, like if I divide this beam into various elements, and if I take an element of the beam, and if I am taking this as a four-noded element, so obviously four-noded element will have bilinear uh, shape functions, and uh, also the mapping, everything is bilinear. So, but like when a beam bends, uh, this element will bend like this because uh, bending will obviously create a uh, curve deformation like this. So this element has to bend like this. But because in finite element, the element which we have taken can only undergo bilinear deformations because there are only four nodes, and the displacement approximation which we use will allow only us bilinear approximation. So because of this uh, uh, beam will will not undergo any deformation, and it will be locked in shear. So that's why this is called as shear locking. So if you take, let's say, instead of four, if you take higher order uh, elements, like uh, you can take eight noded element, or a eight noded quadrilateral, or a nine noded quadrilateral, then that will represent uh, this curved shape better. And but because of increase of degrees of freedom or increase in the nodes, so computational efficiency will be less, like, and convergence will take a lot more time compared to a four noded element. But obviously, you will get a more accurate solution. Let's say if you want to still maintain taking a four noded element itself and to get solution somehow which avoids this shear locking, uh, then there are a few tricks of the game, or like few tricks in the finite element method, which we can use to achieve that and to get a solution. But we are breaking some rules of the finite element in order to get a solution, because of like we can't get a uh, we can't get a solution or a displacement like this using a four noded element, but can we can still somehow manage to get this using some tricks. So these tricks are known as variational crimes. So variational crimes, there are uh, mainly two kinds of variational crimes. One is using incompatible modes, using incompatible modes, and reduced integration. So these are two variational crimes which we use. These are the tricks which we use to get a solution and avoid this shear locking. Okay. Okay. So you guys can hear me?
Yes,
Okay.
sir.
Here. Okay. So last week we have started shear locking and variational crimes. So if you have a beam like this, like if you have a beam like this, and if I want to do finite element, let's say I'll divide this beam into some some number of elements. And if I take an element, so this is an element of the beam I'm taking, and let's say if I take this as a four noded quadrilateral. So four noded quadrilateral, obviously four noded quadrilateral cannot give because the beam bends like this element has to give a deformation profile like this. So if the beam bends, the top and bottom will have a curved deformation like this. But if I have a four noded quadrilateral, so the displacement approximation it can give is only bilinear deformation. Like it can it can just expand in both directions. This four noded element, like this can expand in both directions, but it cannot give a. So these are the kinds of displacements it can approximate a four noded quadrilateral. So but it cannot give a shape like this. So this shape cannot be approximated by a four noded quadrilateral. So what happens is when you do finite element with this, like when you solve the problem with by using the four noded quadrilateral, so you will get this kind of solution where all elements, uh, uh, where all the where all the nodes will have zero solution. So this is called as shear locking because the element is not able to deform and it is locked in shear. So all the nodes have zero displacement. So this is kind of causing a problem. So that's why this phenomena, we call it as shear locking, or you can also call it as parasitic shear. So that's why. So in order to avoid this kind of problem, so if in bending, like if you want to avoid shear locking in this case, So instead of taking a four noded element, I can take a eight noded element, eight noded quadrilateral element, eight noded quadrilateral element, or a nine noded quadrilateral element. So higher order elements will give this kind of curved surface. Like if you deform this element, this deformation, this element can be deformed to this shape, but this cannot be deformed to this shape. Four noded quadrilateral cannot be deformed to this shape. But if you are using this eight noded or nine noded quadrilateral, so what you are doing is like you are increasing computational complexity because you have to do more number of integration, and also you have lot number of nodes. So this will increase the complete computational complexity and also rate of convergence. So when I say rate of convergence, like you should have more number of elements. Uh, so all these issues occur. So it will take more time to solve the problem if we take a eight noded or a nine noded quadrilateral element. So I want to avoid that computational complexity, and instead of using this eight noded quadrilateral element, if somehow I can use a four noded quadrilateral itself, like if I can use this only, if I can use this only and get the solution by avoiding this shear locking. So if I can do that somehow, then it is a good thing because I will because there's a four noded quadrilateral will have lesser computational complexity with respect to eight noded or a nine noded quadrilateral. So I can avoid that computational complexity and my rate of convergence will also increase. So that is what I want to do. So if I want to do that, obviously there are like rules. There are some rules which I have to break. So I can do that by breaking some rules of finite element. So those are called as like variational crimes. So like it is like committing a crime or using some kind of cheat code. Like if you have played GTA Vice City or like some kind of these games, like we use cheat codes to do some task or some kind of uh, to avoid difficulty in uh, playing the game or something like this. So these are like obviously not legal. So but we are doing it somehow because like we want to get the solution in an easy manner and avoid the complexity. So those are called as variational crimes. So there are like basically two types of variational crimes. So first thing is like you can take these incompatible modes and you can also use the reduced integration, which we will see. So if you have, let's say, you have incompatible modes. So, like if I have a four noded element, my displacement approximation will look like this. So, will be equal to 1 to 4 n of x comma y ui. So, n1 u1 plus n2 u2 plus n3 u3 plus n4 u4. So, that is what I will get. Similarly, v is we have two displacement because this is a 2D element. So we will have two displacement. So we will have 1 to 4 n of x, n1, ni of x comma y, vi. So n1 v1 plus n2 v2 plus n3 v3 plus n4 v4. So these are my two displacement field for a four noded quadrilateral. But I want to somehow get this quadratic or like some curved shape in my displacement field approximation. So what I'll do is I'll add some quadratic terms. So those are like or those are in the form of this. So alpha 1 minus x square plus alpha 2 into 1 minus y square. So I want to have quadratic uh, uh, deformation in both the direction x and y. So and similarly here also I will add theta 1 1 into 1 minus x square, beta I 2 into 1 minus y square. So obviously for a four noded quadrilateral, I should not have this quadratic terms, but we are adding it to somehow get the solution which we want. So this is kind of a cheating which we are doing. Uh, so this cheating also should be done very carefully. There are some conditions like strain energy caused by these extra times should be zero. Like if you want to read more about it, like you can go to some text and read about that. There is a text by Professor Manish Rikhanda itself. You can buy that text. So that text is uh, yeah, I have the PDF of it. So so that yeah, I don't have it. See. So you can buy like there is no soft copy available. Like you have to buy that book. The books, the textbooks. The text name is Finite Element Method and Computational Structural Dynamics. Same as the name of the course. Like you can buy online, and also like other books also have these explanations regarding incompatible modes. Uh, so how we can implement this and all these things, so that you can find out. So this is one kind of a variational crime which we can commit to get the solution. So second one is uh, reduced integration. So reduced integration. So reduced integration, what we do is like if you have like we are saying that element is getting locked in shear, right? So basically element is not getting deformed. So because shear strain should be zero. That is the condition which a beam element should satisfy. So because of that, even if you apply load, u1, u2, u3, and u4 will become zero, and v1, v2, v3, and v4 will also become zero. So because the shear strain has to be zero. So that is the condition which we are looking at. So because of that, so like when it translates to finite element, like when you find out like by using this four noded element, if you like you take this four noded element, get the elementary stiffness matrix, force matrix, elementary force matrix, all these things, and so it basically, let's say this is the elementary stiffness matrix and these are the elementary deformations. So U is the U1, U2, U3, and V1, V2, U1, U2, U3, U4, V1, V2, V3, V4. So, and this is the FE, so nodal forces. So, we are saying that UE is becoming zero. So, UE will become zero because it has to satisfy, the element has to satisfy uh, the shear strain and it gets locked in uh, shear. So for that, all the elements of UE, that is V1, U1 to U4 and V1 to V4 should become zero. So if this is becoming zero, so it means that this KE is like very high. So if KE is very high, like let's say if this is like near to infinity, if I take KE inverse into FE, so if this is like near to infinity, 1 by infinity will become 0. So like if K is very high, when I take the inverse, it will become 0. So 0 into Fe will become 0. So in while after like after you do the finite element formulation for this beam using the four noded quadrilateral, you will get this Ke which has a high stiffness. So but whenever we do Ke, like for element, so if I want to find out K11, K22, K12, K2, 21 and K22, So we do this integration, right? So we do we do the integration over the domain. Some this kind of integration we do, uh, some kind of integration you do. So while doing this, we take Gauss quadrature. So we take Gauss quadrature, like if you have based on the polynomial degree you have, based on the polynomial degree you have, like let's say if you have if you want to uh, if you want to uh, take a if you somehow if you have to take a four noded no like four 2 cross 2 Gauss quadrature rule. So you will have four Gauss quadrature points. So then K11 will become, like let's say this is the some f. I'll write it as some epsilon comma sorry eta comma eta. So this entire thing I'll write it as eta comma eta. So then what I'll get is like I can write this as W1 uh, f of eta 1 comma eta 1 uh, like this. So W2 f of eta 1 comma eta 2 like this. So I'll have basically W3 into f of eta 2 eta 1 and W4 uh, eta 2 eta 2. So this is basically like we are converting the integration into summations. So like you can see, like if I drop two or three elements, like if I drop two summations from this, so obviously stiffness will reduce. So if I reduce the stiffness, then it will not be near to infinity. Okay. So instead of using 4 point Gauss quadrature, I can I will just take 1 point Gauss quadrature for this element, and I can write this as W of W1 into epsilon 1 comma eta 1. So like you based like instead of taking like 4 point Gauss quadrature, like or 2 cross 2 Gauss quadrature, I am just taking 1 point Gauss quadrature. So this will give a lesser value compared to the compared to this. So somehow I am playing the tricks here. So this is not accurate. This is accurate. This will give you accurate stiffness, like and this will be equal to the analytical integration if you do here. So this will be equal to that. But if I am just taking one Gauss quadrature point and I'm doing it, I will get a lesser stiffness, which is like not accurate, but like very close to this K11, true K11. So somehow I am like playing the trick, like I'm avoiding the accuracy in order to get a solution. So then if my K is decreasing, obviously it will not be equal to infinity. So if this is not equal to infinity, so this will not become zero. If this will not become zero, I'll get some solution. So this is called a reduced integration trick or a variational crime. So again, if you want to read about it, go and read in some kind of textbook. Uh, you'll get detailed explanation about this. So these are two kinds of things. These are two kinds of variational crimes, because uh, these things you should not do. So these things you should not do. These don't satisfy the rules of the finite element, but we are still doing it to by compromising some accuracy to get some kind of solution. Uh, so that's why these are called variational crimes. So one is incompatible modes and two is reduced integration. So I hope you have understood or got the gist of these things. Okay, if you have any doubts, please ask. I'll explain you whatever whatever the doubts which you have. You can ask me in these things. You can also go through the notes. There is like some kind of explanation given, but this will not be clear. Like if you unless if you go and do some kind of problem or solve it, this will not uh, hit you. So this is like something which you have to experience. You have to some solve some problem by taking this kind of thing, and you will experience this, and then you will get to learn. So I can just say it because I have experienced this and I know how to do that, how to avoid it. But like if you want to completely understand, like you have to go and read some textbook and implement all those variational crimes, how shear locking is occurring. So those things, I would suggest go and uh, have your own study, because this course is just giving the gist of all these things. It is not covering it in a detailed manner. So I would suggest you to do that. So this is one of kind of a problem. Like these are like some kind of questions like which you will be asked if you are like sitting in some kind of comprehensive examination in your PhD, or like if you go to some industry interview. So you might encounter these questions about shear locking, variational crimes. What you do, what variational crimes is nothing but more like what you can do to avoid shear locking, all these things. So then we have also seen some kind of explanation about the patch test. So patch test is like uh, a test like if to see if you can get the convergence. So you get the convergence for your problem by like instead of solving the whole problem. Uh, like if you have discretized your domain like this, like with lot of elements, uh, with lot of elements like this. I'm just giving an example. So you take a small patch in this. You take, like you will just take a small patch in this. Let's say this. I'm just taking this. So you take a small patch out of it. Let's, let's say it may look like this. So this can have quadrilateral or triangle elements. So, but it should have like one at least one interior node. So this is a patch, and this should have some like one interior node at least. And you like there are two kinds of patch test. One is uh, you apply uh, you apply displacements. So like you can apply displacements in various forms. That is also there. Uh, so you apply displacement at the external nodes, and you estimate the displacement at the midpoint, and you see if the displacement is satisfying the finite element uh, constraint. And like there is also another test based on force, like you can apply force or traction on all the on the exterior nodes. So that is also one kind of test. So uh, this is a very helpful tool. Like before going into like when you mesh your problem, like before solving the finite element, like because if you do the meshing and if you go on to solve the finite element problem, probably it will take a lot of time because finite element solutions are not cheap or not easier like to get. Uh, it will take time, so it will not be like quick. So like if you like, let's say if you are running a very complex finite element simulation, like it will take, let's say, probably some 24 hours or like 10 to 10 hours, or it is a lot of time. Like you will just click like you define the mesh and you define the assembly and you like then run like everything you do and then run. So what happens is that sometimes because of some kind of meshing error, you might get an error. So like if you are running the finite element uh, for 10 hours or 24 hours, the simulation is like taking lot of time, and if you are getting an error at the end of it, it will not be like very efficient, right? So instead of doing that, you can do this simple test which will ensure your convergence. So which will ensure you get a correct answer. Like this patch test, you can just do by hand itself. Like you don't need to uh, do kind of a finite element simulation like in just 1 or 5 like 2 to 5 minutes. Like you can just check if the mesh is satisfying the criteria and the elements are good enough to give me convergence. So patch test uh, is one kind of thing which will help you do that and avoid convergence issues. So okay, so okay, so there are, as I said, like you can have a force patch test and also a displacement patch test. So this patch test also has other like uh, other uses, like after you get the finite element solution, you can do posterior error analysis. So that is also there. Like before doing the finite elements solution, we can use patch test to avoid any issues, and after getting the finite element solution, we can do error analysis using the patch test. So there are like many uses to this. So you can again go and read about it. Like it is like available lot of texts. This is available. Like you can solve some kind of simple problems and see what is the patch test. So this was like a brief till now which we discussed, and then we have moved on in this week to plates and shells. So plates and shells, we have not gone uh, like we have not covered everything. So we have covered only plates, and that too only one kind of theory. So which is similar to Euler-Bernoulli beam theory. So that is the Kirchhoff law plate theory. So there is also a Mindlin plate theory or Reisner Mindlin plate theory, which is similar to uh, our Timoshenko beam theory. So these are like different kinds, and also shells is another like ocean itself. Like if you want to uh, know more about that, like you should probably take a course itself. So there are like courses available on theory of plates and shells. Like if you want to understand more about the theories of plates and shells, probably you should go and check those courses. Like there is a course by Professor Tarun Kant of IIT Bombay. It is a very good course. Like he covers everything. Uh, like shells is a bit less, but like in detail about theory of plates and uh, theory of plates and shells. Theory of plates and shells. How do we get the governing equation or the equation of motion of plates, and how you will solve them. So how you take the assumptions. All these things are all these things are available. Like if you want to go and study more, like there are also a lot of books available. I think there is a book by Professor J.N. Reddy, but that is not uh, a very simple one, because like if you know initial notations, like you can read his books. But if you don't know initial notation, probably you can watch this course by Professor Tarun Kant. So that is a very good course on plates and shells. Uh, like there are some kind, like if you can just go to YouTube and search this, you will get plates and shells. I think this is by uh, uh, IIT Bombay has a program. I think there is a program. I think SEEP or something. I can't remember it exactly, but uh, this is not an NPTEL course, but it is there on their YouTube channel. So you just search this and type Professor Tarun Kant, you will get the details. Uh, you can know more about it. It's just like a very big ocean, but we will, but we have to deal with this in a single class. So that is what in single week it has been covered, because like we are not going into detailed explanation of everything. So so I have this book. This is the book which I was talking about. So this is the book, Finite Element Method uh, and Computational Structural Dynamics. So this is by Professor Manish Srikhande itself. Like, so he has like this has a lot of practice sets, practice problems, and also a little bit more of explanation compared to our explanation is explanation compared to our slides which we have, but and also a lot of other areas which we have not covered in this course, like uh, more details are available. Like if you want to buy this, you can go and buy. I don't know if you can buy it, but this is a uh, this is not a, I think this was a gifted copy which my professor had, so I just borrowed from him to study for this course. So no, it is not a simpler book. So if you want to, like, if you have to read this book, probably if you have to read some other simple book, uh, there is a book by Professor Asghar Bhatti. So Asghar Bhatti is a book which is simple, and you will understand it easily. This is not a very simple book. Like if you have already uh, if you have already taken a course on finite element, and like if you have already like if you already know about finite element, and if you want to know more, then you can like refer to this book, because this book covers everything, like every minute detail about finite element, uh, like how like what kind of issues you can get while you deal with finite element. All these things are there, but not in a very detailed manner. So it will not be easier to understand. So like it's not like it's not very easy to understand. That's what I can say. Like even I had to like refer some other books to understand this more. So I would say like, but this will cover everything which finite element has to offer. Like mostly everything in finite element has been discussed, I think. To my knowledge, like I haven't seen a book which has covered like every aspect as this. And this course also, which we are like taking, the NPTEL course also has a lot of details. But the same, like if you take a finite element course, like if you can see some other finite element course in NPTEL, like probably they'll go just till 2D elements or 3D elements, and that will be a 12-week course. So here in 6 weeks or 7 weeks, we have covered that, and like we are going into plates and shells now, and we will also discuss the dynamics of these things. So this course is like not like as I said, like this course doesn't discuss everything in detail. So if you don't know lot of things uh, earlier, like if you have not taken some course on finite element earlier, it will be probably it will little bit difficult for you, because you have to read it again, and you have to redo a lot of things, you have to practice a lot of things, then you will understand these things. So this course is not like very straightforward and simple. It is uh, complex, and it is also vast. So I haven't seen a course which covers these many things because like finite element people just teach only up to 2D, finite element up to 2D, and it will be a like 8 to 12 weeks course, 2D to 3D. Here we are going into plates and shells, and then we are also looking will like in the coming weeks we'll also look at how we will solve dynamics problems. Like up to now we have just solved static problems. All the loads which we have covered, all the loads which we are seeing are just static loads. We have not seen like what will happen to a structure if there is a uh, dynamic load acting. So that is a different thing altogether. So that itself is an another course. Uh, in IIT only, like I have taken a course on computational structural dynamics. So that just deals with the vibrations of beams or continuous medium like plates. So and finite element method. So so that is itself an another course. So this course is like very vast, but the time allotted to each topic is very less. So you have to probably go and read a lot to understand everything, but uh, you can do it. Uh, it's not like impossible, but you can do it. And also like our assignment problems are also like not that complex. And exam questions also will not be that complex. Uh, but you have to go and solve each and every topic which we have discussed. Then you will get everything out of this course. I would say it will be a very helpful course by the end of like you complete this course, and then I think you will be a very good uh, you will have a very good knowledge in dynamics and also in finite element. That is for sure. But you have to work hard, very hard, and like effort is like a lot more when compared to other courses. So that's what I would say. Okay. So so if you have a plate like this, so in plates, I'll just tell you what we will do. So let's say I'll just compare a beam and plate. So you will get a good understanding of this. So beam is a 2D thing, but we make it 1D. Like in our approximation, we will just study about the mid-plane deformation, right? So we study about the mid-plane deformation. We will just take and we make it 1D, and we do the analysis like we have seen like finite element for beams already. So we will do it. So this is a beam. So and each node at a beam, like let's say if I am taking at each like if I'm dividing it into element, so a beam will have a transverse displacement and also a rotation. So each node will have 2 degrees of freedom. 2 degrees of freedom. So this is the beam. So and it will, you know, already like this will bend like this. So this will have a displacement, transverse displacement, and also a rotation. So 2 degrees of freedom are there. So let's say I have a plate. So in beam, like we are saying that my length is very high compared to my cross section dimensions or like the other dimensions, base and thickness or uh, thickness in the two directions. So this is a beam. Let's say if I have some kind of structure, 3D structure like this. A beam is also a 3D, but like yeah, I'm just saying it. Uh, Here there is like some kind of thickness to this. Yeah. So this is the thickness. The thickness of the beam. So now you can see, like, let's say this is L and this is B. So L and B are comparatively very high compared to the thickness here. Let's say this is H. So this is a plate. So here only L was higher. Here both L and B is higher. So a plate, like if there is a load acting here. Okay. So if a load like some kind of load, distributed load or point load acts, beam will bend like this. It will bend in both the directions. So that is the plate will bend in both the directions. So it will, like, let's say if you have a plate like this, it will probably bend like this. So in, so this is kind of the deformation which we can get in plates. So like there is a theory, like there are like various theories, like beam has uh, Euler-Bernoulli beam theory, Euler-Bernoulli beam theory, and Timoshenko beam theory. So in Euler-Bernoulli beam theory, what we assume is plane section remains plane, uh, and it is perpendicular to the. It is perpendicular. This is like, let's say this is your uh, beam after deformation. Like if there are sections after deformation, so this plane section will remain plane, and also this is perpendicular to this mid surface. So this is the Euler-Bernoulli beam theory. When we go to Timoshenko beam theory, so our like our assumption relaxes a bit, and we will make more closer to reality. We assume that still the plane section will remain plane, but this will not be perpendicular, and this will have some like value angle which it makes with the mid surface. This will not be perpendicular. So this is like this we use for thin beams, like when my thickness is like less, when my depth is like depth of the beam is less, and like if I have a thick beam, I cannot neglect shear deformations. So I cannot neglect shear deformation. Like let's say if I have a beam like this, if I have a beam with uh, like this, if I have a beam like this with very high depth, I cannot neglect shear deformation. So that's why I will uh, take assumptions. I will not take the assumption that shear deformation is zero, and I will not assume that my plane section will be perpendicular to the mid surface, and I will include shear deformation. So that's why this is like a better theory which I can use for thicker beams like this, or like beams with higher like large depth. So Timoshenko beam is a higher order beam theory, or like you can also call it as first order shear deformation beam theory. That is also a name. So these are two beam theories which we know. I think you know these two beam theories. Like if you probably, like most of you will know Euler-Bernoulli beam theory, but you might not have heard about uh, like I think you should have heard, but in case if you have not heard, go and read about Timoshenko beam theory also. So Timoshenko beam theory, like in Euler-Bernoulli beam theory, we have two deformations. One is like there is displacement, uh, vertical displacement at each node, and also there is also rotation of the beam, right? So rotation is just taken as the derivative of this transverse displacement, because the plane section is remaining plane and it is normal to the mid surface. So these are my two uh, degrees of freedom, which we will estimate using finite element method in Euler-Bernoulli beam theory. But when we go to Timoshenko beam theory, W will be there. In addition to that, there will be phi. So which I have to estimate. So phi is like here phi is the rotation, and it is not equal to this uh, uh, derivative of or the slope of this W. So that's because there is also shear deformation in addition to the bending which is happening. So that's why like this and this will be different. So Timoshenko beam theory will involve this. So that's why like you have to uh, like read about it more. Timoshenko beam theory. It is a very it is like complex compared to the Euler-Bernoulli beam theory. Euler-Bernoulli beam theory you can only use like if your beam looks like this. There are like some conditions uh, like can read like depending upon like if your thickness if your depth is less then you can use the Euler-Bernoulli. But if your depth is more, you have to go for Timoshenko beam theory for better results. So this is about beams. Okay. So when I go to plates, if my plate has like less thickness, like if I have a plate like this, a plate like this, like thickness is less. But if I have something like this, a plate with like more thickness like this, I'm just exaggerating, okay? But the thickness is more. Uh, then I cannot like I like for this I can use the Kirchhoff love plate theory. So that is what which was discussed in this uh, week's lectures, Kirchhoff love plate theory, and we will limit our discussions to this only in this course. But if you have a like a thicker version of the plate, so you cannot use this. So you have to go for Reasoner Mendlin plate theory. So, or you can also call this first order shear deformation plate theory. So this is for thick plates. So this is for thin plates, and this is for thick plates. So our course has only covered this. So if you want more details, you can go and read about this. As I've said, you can go and watch lectures of Professor Kandan Kant, or you can also read some kind of textbook related to that. So uh, each like what we do is like we take this plate in the Kirchhoff law plate theory, and we will just take the mid surface, and we will just uh, will consider it as a 2D plate or 2D shear element, 2D uh, plane stress element, and we do the analysis. So this is the mid surface of the plate. So you write uh, uh, the diagram uh, like we will have the like we will write all the stresses on our plate, and take moment equilibrium, force equilibrium, and like doing all these things we will get our equations. So and I think like you can go and check those on the text or the lecture slides which are provided in the portal. So I won't discuss like how they came. Like I will just go through the procedure. So, but you should know that plate can bend in both the directions. Earlier, it was only bending like the beam was bending only in one direction. So plate can bend in two directions. So that's why like I will have at each node like if I'm dividing this plate into like lot of elements. So uh, at each node I will have a vertical displacement, transverse displacement, and let's say this is uh, slope in one direction, and like my beam can also bend in other direction, right? So in two directions it can bend. So this is, let's say, dou x, dou w by dou x, and this is dou w by dou y. So at each node I will have 3 degrees of freedom. So this is w. You can also call it as theta x. This is also called it as theta y. So at each node you will have 3 degrees of freedom compared to our uh, beam. We had only 2 degrees of freedom at each node. Here we'll have 3 degrees of freedom. So that is the difference we are getting. So you can go and like if you want to learn how we are getting the equations of plate, so that is a more like a very detailed process. We have to follow the procedure. So like taking the assumptions of Kirchhoff law plate theory, like assuming that a plane section will remain plane. So this is like Kirchhoff law plate theory is equivalent of Euler-Bernoulli beam theory. So these will have both same assumptions. So Kirchhoff law plate theory and Euler-Bernoulli beam theory. Okay. So you can, like when you read Kirchhoff law plate theory, you can compare this with Euler-Bernoulli beam theory. You can also see that here also the rotations are derivatives of the transverse displacement. When you go to Reisner-Mendlin plate theory or first order shear deformation theory, this will not be equal to these derivatives. So because we will include shear deformation there. So as I've said, I will just write what is the final governing equation which we get. So the final governing equation after considering this plate theory, like after formulating this plate theory, is something which looks like this. So this is my final governing equation of motion. Governing equation or equation of motion, whatever you can write. Equation of motion. If there is also dynamics involved, but let's say yeah, we'll also consider dynamics. So this is my final equation. Final equation for the analysis of plate. So if I solve this equation, I'll get how the plate is deforming. Or I'll get W basically. Based on W, I can tell how the plate is deforming at various points in the domain. So Q is like some more load acting. Q is some load acting on the plate, distributed load, and rho is the mass density, H is the thickness. So here T is the time derivative. So, but obviously we will not, we have not gone still into, or let's say I'll just not write this. Okay. Not write this. I'll just write this as D into this equal to 0. This is my equation, governing equation for the plate using the Kirchhoff law plate theory. So this D has a value which is equal to EH cube by 1 minus mu square. This is also called isotropic plate rigidity. So like in beam we have EI, right? That is flexural rigidity. This is plate rigidity. So isotropic plate rigidity. You can say this is equivalent of EI in beam. So that is my equation of motion. So in finite element, like we want to do, like we are studying finite element. So like if I want to solve this, like I have to probably solve this differential equation, partial differential equation. If I have to solve this analytically, it will be a huge task. So we have seen like how we probably like we all have done bachelor scores on this finite element, not finite element. Mathematics, I think in mathematics one, in your BTech, you might have like learned various techniques to solve differential equations. Uh, there are like you can lot of techniques we use we get the complementary solution, particular solution, all these things, like various things are there, but like not every time you can do that. Like analytical solution is not possible for every uh, domain. So we have to go to some kind of numerical solutions which are easier, which can be done by computers. So that's what we were looking at. Like we have seen this for a bar and a beam, and we have also seen for 2D elements. So now we are going further into plates. So so obviously in finite element, we will assume some kind of displacement. So W is something which I will assume. So if I assume W, there will be like obviously this is not equal to the real solution, right? Like W of xy. So I will assume something. So that solution, if I substitute in this, if I substitute in this, it will not be equal to zero because my W is not exact. So that's why it will have some error, which we call it as residual, right? So this will give some residual. So that residual we have to minimize. So for that we use the weighted residual method. So we have all seen. So let's say uh, let's say my domain, because this is a 2D, like I'll just take 2D domain. So W into my governing equation, like governing equation is like everything here. W into governing equation, P will become zero. Or you can say this is, I can also call this as residual. W into residual, because this will not be equal to zero. So there is some residual. So in this, if I substitute if I substitute this, I'll get some residual. So that is what we do. So again, after doing this, we can take the Gauss divergence theorem. You have already seen, we have already seen in the 2D finite element. So we can use the Gauss divergence theorem, like which is similar to doing integration by parts in 1D, and do simplifications. And then finally, we will get this kind of equations uh, which we can use. We will get finite element equations and also boundary conditions. So that have to be satisfied. Okay. So we already have looked into it. I'll just skip everything and I'll just uh, write how my K and uh, this will look like. So let's say, because uh, first I have to assume the solution, right? So first I have to assume the solution. Let's say W of xy. I will assume, because I have how many, let's say I'm just taking one element. I'm just taking one element for full plate. At each node, I have 3 degrees of freedom. 1, 2, 3. That is W1, uh, W1, dou W1 by dou X, dou W1 by dou Y. Similarly, W2, rotations in both the directions. W2, similarly for 3 and 4. So total I have how many degrees of freedom? 12. So 4 into 3, I'll have 12 degrees of freedom, which I have to determine. So I want basically in this the solution, which like the polynomial which I am taking, I should have 12 terms. So if I'm taking this 4-noded plate element, I should have 12 terms. So that's why this will look like this. So this will This is basically like you take the Pascal triangle and do those all these things. So this will look like this. So x square a5 y square is a6 x cube plus a7 x square y plus a8 x square xy square plus a9 y cube plus a10 x cube y. This is a, sorry, not 9. Don't confuse it. And a11 xy cube. So my solution approximation should have at least 12 terms. So it should have 12 terms. So those are all the 12 terms which I'm taking. So now I want to find out the shape functions. So we have already seen how to find out shape functions. So if I have w of x comma y, okay. So this is my approximation. So I'll substitute like all the 4 points, the coordinates of all the 4 points I know. So or let's say I'll just take all these terms of x, y, x square, y square, uh, x cube, x square, xy square. So we know the Pascal triangle. So this is everything based on that. Cube, x cube, xy cube into a naught. I can write this w of xy as this. So a naught, a1 up to a12. Okay. Sorry, a11. A11. There are only 12 terms. A naught to a12. So if I know, and also let's say I also have uh, uh, derivatives, right? So I should also do dou w by dou x. So that will give me some a1 plus 2a3 x plus a4 y, something like you just do the differentiation. Dou w by dou x also will give me some a2 plus a4 x. So you can do it sometimes. So I have a like uh, I will have basically I'll have basically I have to find out, like, let's say 12 displacements, right? So 12 degrees of freedom. So that will be dou one w by dou x1, or you can, I'll just write it as comma like this notation. Probably you should know at x1, uh, at y1. So similarly, this is up to w w12, not w12, w4, uh, x4, y4, equal to at each point. At each point, I know the x and y coordinates, right? So I know the x and y coordinates. So I will just substitute the coordinates. So so you will get some kind of matrix which is known as the C matrix or the coordinate matrix. So we know we have already seen this, how to build the shape functions, right? So and we have a naught, a1, a2, up to a11. Okay. So I know the coordinates. So I'll get something like this. So, or let's say this, I can write it as WE, or the deformations at all the nodes, including the transverse deformation and also the slopes, will be equal to C into A. So A is nothing but this vector A1 to A0 to A11. C is the coordinate matrix. So, but we know that W of V comma X comma Y is equals to P into A. So So P is nothing but this. P. Okay, this is P. So from this, what I can do is I can take A is equals to A is equals to C inverse of WE. Okay, so I'll substitute here A is equals to C inverse of WE. This is a vector. Okay, this is a vector and this is a function. Okay. So if I do P into C inverse, I'll get my shape function. So that is N into WE. Okay. So this N matrix will have like how many 12 cross 12. This is uh, this is 12 and the C is also, yeah, 12 cross 12. So I'll get this is 1 cross 12 into 12 cross 1. So I'll get a matrix N matrix which is of shape N into 1 cross 12. So I will have basically 12 shape functions. So this is how I can get the shape functions for our finite element for the plate, finite element of the plate. So that is the procedure. Okay. To get the shape functions. I hope that is clear. Do you have any doubts in this? How to get the shape functions?
I have one doubt.
Yeah, yeah,
Supposing you want to do this in terms of zeta eta coordinate by using that isoparametric,
yeah, yeah, yeah,
whether you will get the same answer. I mean, can you take that approach also?
yeah, yeah. We also use distorted elements in plates also, uh, but that becomes more complex. You have to do the mapping properly. Uh, that also can be done.
Okay, okay. So
Yeah,
this is a better approach, PC inverse.
yeah, yeah. PC must be the better.
Okay,
Uh,
thank you.
think so, but we, uh, okay. Yeah, I think we can do isoparameters. Yeah, there is also these things are also given in the textbook, so you can do it. Okay, so this is how we get the our shape functions for the plate element, and after we get the shape functions, we can use the Galerkin weighted residual uh, element or like the our weak form. So our weak form actually our weak form looks like this actually. So this is derived. Like you have to refer to the uh, notebook or some textbook or the slides. So this is our weak form. Uh, this into uh, n. So instead of w, I am replacing w with n here. And you have this something like this. Like this is the normal force. Uh, these are all the boundary conditions. We will we can avoid this. Like we will see how we can do that. So this is B gamma. So this is for the boundaries. So gamma is for the boundaries. And next, I'll go to the domain or the main equation, which comes in the form of Ke into Fe, K into U, W is equals to Fe. So this is the integral which will give me the nodal force vector. Q is the surface uh, distributed force which is acting on the plate surface in the transverse direction, and, and this is the uh, this is the notation which we are using. Like, I'll tell what these notations are. So W is the vector, nodal force, nodal displacement vector, or the element displacement vector. So it will have 12 elements. So that is what we have to find out. Plus, uh, I will leave the time domain part. So this will be equal to 0. So this is my weak form. Okay. So in this weak form, this is already, yeah, this I have already put equal to 0. So in this weak form, this is the boundary conditions, natural boundary conditions. We can call them natural boundary condition. And this is our equations which we get, the governing equations which we have to solve. So equations to solve. So here I have to get the stiffness matrix and the uh, displacement matrix on the displacement vector and the force, nodal force vector, right? So this integration will give me the stiffness matrix, and this will give me the nodal force vector. So finally, I'll get something equation which looks like this: Ke into Ue is equals to Fe. Or let's say I'll call it QE or FE, you can whatever you want to call it. So elemental nodal force vector. So this Ke is nothing but this integration over. So this you can also write like this D transpose D bar B dt. So B is nothing but L nabla. So this symbol is called as nabla. So this is not delta. Delta is this. So this is nabla. Okay. So nabla is something which uh, you get uh, here, like while we describe this things. So QE is nothing but this and transpose U T omega. So this gives me the nodal force. So WE is UE or the UE or WE is something which we have to find out. So L is this. Uh, so L is this. So this is the L matrix. It looks like this. Over dou x. Okay. And this is my nabla. So these are operators. Okay. Differential operators. So this is my nabla. So if you substitute these things and do these integrations, you will get Ke into W is equals to QE. So our end goal is to find out WE. So we know here already how to derive the shape functions. If we know the shape functions, we can get K. Obviously, this is a simple thing now. So you get the K, you get the stiffness matrix. If you know the surface force Q, what is the load acting on the surface, then you can also get what is the nodal force on the plate. So on the plate element. So you know the shape functions, you get the stiffness matrix, you get the load matrix. You have both the stiffness and the load, stiffness matrix and the load vector. Then you can simply do the inverse of K, and you can get your uh, nodal displacement vector of the element. So that is what it is. Like you have a differential equation which you have to solve. In this case, this is the governing equation of the plate. You do this weighted residual and apply Gauss divergence theorem. Then you will get a weak form. So the weak form, weak form will look like this. So this is the weak form. So from the weak form, we can get our formulation for the finite element. So we'll get the natural boundary conditions and also the weak form. So from that we can do the integrations to get our stiffness matrix and also our uh, nodal force vector, and then by solving it we can get our nodal displacement. So the methodology is clear. Do you have any doubt in this? So the first step is you have to find out the shape functions. So first we have to find out the shape functions. Okay. Then we have to go and get this elementary stiffness matrix and the nodal force vector. Okay. This is the second step. Then after you apply the boundary conditions, so the essential boundary conditions, you will get this nodal displacement vector as the solution. Simple thing. You have to get the shape functions, derive the shape functions, get KE, and QE, and like if you have only one element, then you just go and solve it. But if you have, like, let's say multiple elements, then you have to do also the assembly of the stiffness matrix. So do the assembly and then finally get your global displacement vector. Okay. So that's how we can solve the plate problems. Like this is like the procedure is like same. Even if you go for bar, beam, everything is same. The shape functions will change, and integration and these things will change. But uh, at the end, you will get some algebraic equations. Uh, I mean, let's matrix equations that you have to solve to get the solutions. Okay, so that's what we are doing here. So I have just skyrocketed everything because like I cannot explain the plate theory and everything, but I have told how to get the displacement, how to get the shape function. That is the most important thing. If you know how to get the shape functions, you can probably solve it. So assembly and everything, So I don't need to explain it again. Like you all know. But only the thing which you have to take care of was this to get the shape functions. Now we will see. So this is my problem. So I have a displacement. I will have to find out the displacement at the midpoint of an isotropic plate. So let's say this is my plate. This is my plate. Okay. And I want to find out what is the midpoint deflection at this. Basically, I want to find out W here. I want to find out this W at the midpoint. So they have given some kind of load is acting on this. So load is obviously if I look at the top view, this will look like dots only. Like I cannot, like if I look at the side view, this will look like this. So this Q is given as 3 kilonewton per meter square. And they have also given this other details about the thickness of the plate, uh, uh, E, which is 200 gigapascal, and nu, which is 0.25. So they are telling use four uh, four plate elements. Non-conforming plate elements is something uh, which we use, like you can say the elements which we are using for Kirchhoff law plate theory are the elements. Like they are asking us to use the Kirchhoff law plate theory element. When you go to first order shear deformation theory or Mendelian plate theory, the element will change. Okay, so here we are dealing with only Kirchhoff law plate theory. So that is what this means. Like the elements are non-conforming. So uh, they are telling to use at least four plate elements. So I can divide this into four equal elements. So and I have to find out what is the displacement here. So if I know uh, the nodal displacement at this point, I will get the midpoint displacement of this plate. So they have not given the boundary condition. So I will take all the elements, all the ends, all the ends of the plate are clamped like this, or let's say clamped or fixed. Both are like synonymous words. Remember. So in this 2D or 3D case, we call it as clamped, but like in 1D case, we call it as fixed. So it means at the boundary, W is 0 and also WY, WX is equals to 0 and also WY, WY is equals to 0. So that is what clamp means. So here, like as we have, like we can be, let's say this, I can take this as 0, comma 0, or let's say this point, I can take this, I'll start from this, I'll take this as 0, comma 0. And this is 0, comma 1.5 because my plate is having a dimension of 3 cross 3. So I will take these points 1.5, comma 0 and 3, comma 0. And this is 1.5, comma 1.5. And this is 3, comma 1.5. This is 3, comma 3. And this is 1.5, comma 3. So this is can call P1, P2, P3, P4, P5, P6, P7, P8, and P9. Don't worry about the order of numbering. Like, don't ask me why you are not taking anti-clockwise, because doesn't care, because like I'm just having one element here. Like this whole plate is not one element, but this is one element. Okay, so this is one element. No, don't worry about the node numbering because we have only 4 nodes. So whatever the thing which we have used, like we know the node coordinates for each element. We know the node coordinates. We know the node coordinates for each element. I have to get the shape functions. So n1 is for element 1. I'll get for element 1. I'll get 12 shape functions. Similarly, for element 2, I'll get 12 shape functions. For element 3, I'll get 12 shape functions. I know 4 node coordinates for each element. The coordinates are there. So the coordinate matrix is known, which is C. I know P and C inverse, and I know WE. So if I do P into C inverse, I'll get this shape function. So the coordinate matrix for first will be different. For the second element, element will be different. For the third element will be different because the nodes are different, right? So these coordinates are different. So C will change according to that. So you will get 4 shape function, four shape function matrices. Each will have 12 shape functions. So that we have to determine. Okay. So then after determining the shape functions, we have to determine the next step is to determine the elementary stiffness matrix. So elementary stiffness matrix, in order to determine elementary stiffness matrix, first I have to determine B, right? So B is nothing but this we know, we have seen, that is L nabla, L transpose, something which we have seen already. So yeah, L delta, L nabla N. So L nabla N, that is B. So that will look like this. So that will look like this. So up to dou square N12 by dou x square. So dou square. And this will go on till uh, like this, x square, y square, and xy. This will have 3 cross 12 matrix. This you will get a 3 cross 12 matrix. Okay. So similarly, for say element 2, you will get some B matrix, because the element 2 will have different shape functions, right? N1 of element 1, or you can write this as N1 here, N11, or you can avoid. So you will get B1, B2, B3, B4. Okay. B1, B2, B3, B4. So if you know B, then you can find out this elementary stiffness matrix. For 1, this will be this. For 2, this will be B2. And for 3, this will be B3. And you can also find out the elementary node vectors for each node, for each element. You can do this. You can do this. So this is N1 transpose D omega like this. You can do this, and you can get, for each element, you can go to the nodal force vector. Okay. So you will get K1, K2, K3, K4, and you will get Q1, Q2, Q3, and Q4. So for 4 elements, we will get 4 stiffness matrix and 4 nodal force vectors. And then we have to go for the assembly. So assembly is like, we have to take like whatever the nodes which are overlapping. So we have to sum those stiffness elements, right? So wherever the nodes are overlapping, we have to do the assembly according to that. I hope you already know what is assembly. So we have to do the assembly. You have to write the code. Like this, I cannot explain uh, on the paper because it is like a little tricky, but you can write assembly code. So based on this, you can, like, let's say I have some K1, there will be some overlap because if K1 and K2 are share like, let's say this is K1, this is K2, element 1, element 2, element 3, element 1, element 2, element 3, and element 4. So element 1 is sharing nodes with all the 4. So whatever the nodes it is sharing, all have to be taken care. So element 3 has to be is sharing, like, so each element is sharing nodes with everything. So you have to write a logic mapping so that you can do this mapping. You can do this. Okay. So you will get a global stiffness matrix by the assembly, and then you will also have this global nodal vector, and you will have global force vector, which is QG. So if you solve this, you will get K inverse G into QG. You will get the nodal for displacement vectors on the plate. So how much this stiffness matrix will be like having a shape of, uh, because I have how many? 1, 2, 3. 4, 5, 6, 7, 8, 9. So 9 nodes, and each has 3 degrees of freedom. So I'll have 27 uh, degrees of freedom total. So this 27 degrees of freedom I have to find out. But because this is already clamped, so how many nodes are fixed here? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8. So 8 nodes are fixed. So 24. So 27 minus 24. I can eliminate how many? 24 nodes I can eliminate. I just have to find out only uh, 3 deformations, which is the W at center, slope at center with respect to X, and slope at center with respect to Y. So I'll get a finally I have to solve a 3 cross 3 system. So by doing the static condition, I hope you know static condensation. Wherever the whatever the terms in WG is nothing but W1, W2 to let's say W12. Uh, and you also have uh, sorry, how many? Let's say uh, like W2. I'm just assume that this will have all slopes and displacements at each node. So you will have 27, right? So whatever displacements are becoming zero, you can all just remove those equations. Okay, that is called static condensation. So if I remove those equations, I'll get a 3 cross 3 matrix after static condensation, and WG will be 3 cross 1 because only at center nodes the displacements are not zero. So that's fine. I'll remove all the rows and columns in K which have uh, uh, which have zero displacement, which are coinciding with the zero displacement. So that is what static condition does. And similarly, Q also we have to remove those rows which are coinciding with this nodes which have zero displacement. So if I solve this 3 cross 3 matrix, 3 cross 3 system, I'll get what is the deflection at the center of my plate. So that is what solving that is how we can solve it. So the simple trick which I can tell is, like, when you do the assembly, like, don't do 27 cross 27 matrix. Instead of that, just take the elements, just do like addition only here. Okay. So because you know what is the stiffness terms in element 1 which will occur at this node. You know what are the stiffness terms which will occur at this node. So take those and just sum it, and you will just directly get a 3 cross 3 stiffness matrix. So instead of like assembling a 27 cross 27 matrix, just do that. It will be time saving uh, for you to solve. So that's how we can solve this. I think the assignment also has a similar problem, I think, in this way. Uh, yeah. Here we have only 2 elements. So only 2 elements are there. And in that, like, 2 sides are fixed for the plate. So we don't have to like worry about those nodes. So finally we'll get a 6 cross 6 matrix. So we have to solve the 6 cross 6 matrix to get our solution. Okay. So we have to find out the values of shape functions at n1 and n shape functions n1 and n3 for element 1. So I have told how to find out the value of shape functions. So you can do that. That is not a big task. I think P into C inverse is something which you have to do. So for each element they are asking. So then First two questions are done like that. Third question is strain components evaluate at the midpoint of element one. Okay, so this is something uh, which you have to read and solve. So you have to basically solve the finite element equation 6 cross 6. Then you get the strains from that. After you get this, oh sorry, then you get the displacement field from the like from the nodal displacements. You get the displacement field W of x comma y, and then you do differentiation to get the strain components. So at the top surface, and yeah, layout at the top surface. So yeah, these are four questions. First two are very simple. Third and fourth are little bit uh, tricky. Not that much, but yeah, you can do it. So it's not. Yeah, the plate given by the plate defines. Okay, so this uh, already already these displacements are already given. So you don't have to like solve the finite element equation here. So you just have to get this W of xy for uh, element one and W of xy for element two. So we have n1 u1 sorry n1 w1 plus n2 do1 w by uh, like this, right? So how many like we'll have 12. We'll have 12. So in this lot will become 0. So we will like lot of displacements are 0. So you can remove that. You have already found out the shape functions, and there are also substitute those shape functions, and there are also nodal displacements which are given. Substitute those nodal displacements, you will get W of xy and W of xy of second element also. So then you do differentiation, like I think epsilon xx and epsilon yy, you know these things. So I think epsilon xx is something like here, yeah, epsilon xx is this z into dou square w by dou x square. Epsilon yy is z into dou square w by dou y square. So substitute this here, substitute in these equations for element 1 and element 2, and we also have to find out gamma xy, right? So yeah, gamma xy. So this is this. So at the top surface means you have to basically uh, substitute here the value of z as uh, h by 2, h by 2, which is our thickness is h, and h by 2 is like half of the thickness. So by that way you can get the three different strings. This is clear, like what I have told. The procedure is clear. Do you have any doubt in this? How to solve this problem? Clear? Am I audible? Okay. Okay. So first thing is you have to find out all the shape functions for element 1 and element 2. 12 shape functions you have to find out. There is no other way. Like you have to find out these shape functions doing P into C inverse. You can write a Python code or do something like do hand calculation if you have patience. Uh, whatever, like MATLAB code, whatever you want to do, you do. Then here the nodal displacements are already given. So for fixed, this will become zero. For fixed nodes, this will become zero. And for the free nodes, they have given the nodal displacements for element 1 and element 2. Substitute those. You substitute N1, N2, and L12, and also substitute the displacements which are already given. You get W1, then you can find out the strains at the top surface at the middle of the element. So middle of the element means you have to find out the corresponding xy value for the mid point of element 1 and element 2 and substitute that, you will get this strains. Similarly, do it for element 2 also. So that's how it is. That's how simple it is. Okay. Uh, Next week, I'll also share the code for solving a plate finite element. Uh, this whatever I have explained here, like how to do it in Python. I'll give the code. Next week you can play around with it and understand it more. I could have given today itself, but there are like some errors in the code which I have to solve. Uh, because this is also my first time. I know the theory of plate extensions, but I have not implemented finite element on plates. So I'll rectify those and I'll share the code with you. I'll also explain the code in the next class for a few minutes. Then we will move on to the next thing. So there is a much simpler, part of the course in the next week, which we have to uh, go through solution of linear equations. So this is something which we have already uh, studied. I think the LU decomposition, QR decomposition, I think all those things we will learn. So what are the different things to solve linear equations? So those things we will discuss in detail in the next week. You can also probably get a revision of your linear algebra, which you have, if you have studied, that you can get a refresher of that. So linear algebra is very important. Like if you are someone who wants to do numerical methods or like simulations as your work, linear algebra is very important. Like even if you want to like explore some kinds of fields like machine learning, like if you want to use machine learning in your work or data science, that is entirely linear algebra. So whatever we do, like even ChatGPT is just linear algebra. Like whatever they do, that is linear algebra. So neural networks are just linear equations. Like you can write them as matrices and do that. So that's what this week's discussion was about. Yeah, this was like, as I said, this course is like not very detailed. This course has a lot of content, but not everything is explained in a detailed manner. So you have to basically go through everything, study them properly. Like if you want to understand each and everything which has been taught, like you have to go take some text. As I said, you can refer to this also, refer to this book by Professor Manish itself, Professor Manish Srikangan, Finite Element Method and Computational Structural Dynamics. I don't know if you can get it online. Probably you can get it in this website. Like if you just search it, you will get. You can order it. The cost of it is around 600. But this is not a very simple book. But everything related to finite element, most of the issues which you face, most of the tricks and all the details have been covered in this course and also in this book in a very detailed, not in a detailed manner, but like exhaustively, all the issues have been covered. So if you get to read this book and understand everything, you will be an expert, very good expert in finite element method, along with uh, dynamics also. Like so, you can read it. Like you can accompany some other like you can take some other book also, a simpler book to understand if you are not understanding simpler concepts like there is Asghar Bhatti, uh, which I can think of, or like you can also watch some other uh, courses to clarify, like for plates and shells. Like if you want to learn more about plates and shells, uh, you go to NPTEL lectures, or like there are lectures, YouTube lectures by Professor Tarun Khan. So you can supplement your knowledge. Okay, so that's what it is. Like, do you have any doubts? Any other doubts regarding this week's content, or uh, something which you want to know?
I have one question regarding examination regarding.
Yeah,
Like here in assignments, we are solving like many questions. We need to resort to some MATLAB or Python.
yeah, yeah.
Okay, so in exam, whether such a thing is will be there, or it will be questions will be like much simpler, which we can calculate by hand. Any idea?
Uh, I don't have idea about this. Probably have to. You can ask this question in the portal, uh, because I don't think you will be given access to MATLAB or something in the exam. Probably all the questions which you get uh, will be calculator based questions. Like calculator will be also. Uh, I think you can take the calculator. Uh, I think that is the. I'll just see what is last year's. Okay. So the last year's exam format. This was in October 2024. Uh, okay. Okay. So last year, this course had a pen and paper exam. Uh,
Okay.
so you have to solve. Uh, but you can, like, obviously you cannot. Uh, those will be like questions which you have to like basically use calculator and solve. So you can like no coding. Coding is not something which you will be asked. So I that much I am sure like coding will not be asked. So
Okay. So it's not a computer-based test last year. What was there?
last year it was not a computer based test, but I don't know what will be the format of this year, because last year the assignments which were asked also were pen and paper. Like you had to write, solve the assignment and submit. Uh, because this year the assignments are also like you have to just give the answer. You don't have to write and submit. So I think it might be an online computer based test like this only, but you just have to substitute the values. You don't have to write and solve and submit. Uh, but I don't know still. Like you have to, you just ask it in the portal once. You
Yeah,
might, yeah. Uh, but like anyway, you don't need to do coding. Like if either it is a computer based course or offline paper, pen and paper based course, pen and paper based exam, you will not be asked to do coding. Like that is not possible.
yeah,
Uh,
fine.
yeah,
Okay.
yeah.
Thank you.
Okay. Any other questions? Yeah. Okay. So if there are no questions, we can stop it here today. We'll meet again in the next week. We will see also a code for plate using finite element Python code. I'll explain and also share with you in the next week that you can take and play with uh, to solve different problems. And then we will also look into solution of simultaneous linear equations, basically linear algebra, basics of that. So that will also, which has been covered in the next week, that will solve some problems and look how each method varies and how we can use different methods. Okay, okay guys. Thank you for joining. Have a good night. See you all in the next week.